Happy day. So today we are going to see mathematical modeling of population growth models. So before I go into the topic, let me explain what is a model, what is modeling, what are the different types of modeling, what is mathematical model, and why we go for mathematical modeling. So a model is a representation to visualize something. So models usually are of two types. Either the model can be physical model or it can be a schematic model where we visualize the real world phenomena using graphs, organizational charts, GPS, etc. In real world situations, models are used to represent more complex situations. In all sciences, models are used to represent usually a more complex and detailed reality of the behavior of the system and the activities involved in it. This may be done by using verbal arguments, by drawing, or by physical structure or mathematical formulae. Modeling is a process of representation of a model which includes its construction and working. Based on the domain concept that we use, modeling can be classified into different types like physical modeling, biological modeling, chemical modeling, dynamic modeling, computational modeling. Mathematical modeling essentially consists of translating real world problems into mathematical problems, solving the mathematical problems, and expressing the solution in the language of the real world. The mathematical relations can be algebraic equations, transcendental equations, differential equations, difference equations, integral equations, or even you can have inequalities. So why we go for mathematical model? Many laws of nature, as we know, are beautifully captured and explained using mathematics. And no field in science and technology today is untouched by mathematics. Also, the quantifying some abstract behavior of real world phenomena is made possible using mathematical modeling, which is the main reason for which we go for mathematical modeling. So mathematical modeling through differential equations arises when we have some continuous variables varying with respect to some other continuous variables, and we have some reasonable hypothesis about the rate of change. In particular, mathematical modeling using first order differential equation arises when we have one dependent variable, say x, depending upon one independent variable, say y, and the hypothesis is about the rate of change dx by dt. The two main models that are describing the population growth models are exponential growth and the logistic growth. So first let us have a look into the modeling of a simple population growth model. Simple population growth model usually occurs under ideal conditions where there are unlimited resources, adequate nutrition, no predators, etc. Hence, the population growth won't be affected by the external factors. The population is also considered to grow continuously. That is, the time step we are using is infinitely small. So, let n of t denote the number or the size of the population at any time t. N of 0 denotes the initial population size and b denotes the birth rate. So, birth rate here we refer to the per capita birth rate, that is the number of individuals born per individual per unit time, and d denotes the death rate, which is also per capita death rate. Now, we need to find an expression for finding the population at the time t plus delta t, which is given by n of t plus delta t is equal to n of t plus b delta t n of t minus d delta t n of t. That is, if we need to find the population at any time t plus delta t, we take the current population, which is n of t, with it we add the number of births that is happening in the time interval delta t and subtract the number of deaths which is happening in the time interval delta t. So this is the basic equation which governs a simple population growth model. Now this particular equation can be modeled as a differential equation. Now when we consider the next line there, n of t can be taken to the other side. So we have n of t plus delta t minus n of t is equal to B delta t n of t minus D delta t n of t. Now dividing both sides by delta t and letting delta t tends to 0, we arrive at the following differential equation: dn by dt is equal to b minus t into nt, which is a basic first order differential equation governing the simple population growth model. Now solving this differential equation, we will be able to obtain an expression to find the size of the population at any time t. So using variable separable method and integrating both the sides between the limits 0 to t, we have n of t is equal to n of 0 e power b minus d into t, which is the expression for finding the population size at any time t. Now in this expression, suppose we substitute or we replace n0, that is the initial population, by an initial amount which is deposited in the bank, then n of t describes the amount at any time t where the interest is compounded continuously at the rate r, which is equal to b minus d. So simple population growth model is also called as Malthusian model, and this clear graph given in this particular slide clearly explains how the size of the population varies with respect to time. When b is equal to d, that is when the birth rate and the death rate are same, then the size of the population at all time remains the same as the initial population. So we get a straight line in the graph that is given over there. Similarly, when your birth rate is greater than your death rate, that is b is greater than d, then the population size grows exponentially unbounded. When b is less than d, the population size decreases exponentially, which is clearly depicted in the graph. Now we have an application problem where we apply the solution which we have already derived in the simple population growth model. It is given that the initial population of betas is 3000. In 1 month period, we record the number of births to be 400 and number of deaths to be 150. We need to estimate R, which is equal to B minus D, and project what is the population size in the next 6 months. Now, as per the equation which we have already written in a simple population growth model, suppose we need to find n of 1, that is the size of the population in a 1 month period. It is given by n of 1 is equal to n of 0 plus number of births minus the number of deaths. So we have n of 1 is equal to 3000 plus 400 minus 450, which is equal to 3250. This is the population of the betas after 1 month period. Now we need, using this, we can find out the value for R. Already we know that n of t is equal to n of 0 e power b minus d into t. In this particular expression, when we substitute t is equal to 1, we will be able to arrive at the value of b minus d, which is equal to 0.0800. Now again applying the same equation and substituting t is equal to 6, we will be able to calculate the population size of the betas in the next 6 months. So n of 6 is given by n of 0 e power rt. So substituting the values there, we get 4848 betas in the next 6 months. So now let us consider 2 more factors which affects the population size added to the simple population growth model, which is nothing but the emigration and the immigration rates. Now suppose let I represent the immigration rate and E represent the immigration rate. Then using the same equation which we have used in the simple population growth model, n of t plus delta t, that is a population size in time t plus delta t, is given by n of t plus the birth that is happening in the time interval delta t, which is given by b delta t n of t plus I into delta t, that is a number of individuals emigrating into the population in the time interval delta t minus the number of deaths that is happening in the time interval delta t minus the immigration in the time interval delta t. So this is the equation which governs the population growth model with immigration and emigration. Now this equation can also be arranged as a differential equation and it can be solved to arrive at the expression for n of t. So proceeding by the similar procedure as we have seen for the simple population growth model, taking n of t to the other side and dividing both sides by delta t and letting delta t tends to 0, we arrive at the differential equation dn by dt is equal to b minus d n of t plus I minus e. Now replacing b minus d to be equal to another constant a and I minus e to be equal to k, we have dn by dt is equal to a into n of t plus k, which is the differential equation for this particular model. Again it is a first order differential equation and the equation can be solved using variable separable method. So proceeding by variable separable method and integrating between the limits 0 to t, we have the solution for the differential equation to be n of t plus k by a is equal to n of 0 plus k by a e power at. This is the basic equation to find the size of the population at the time t when we have the birth rate which is a constant, the death rate which is constant and the immigration and the emigration rates are given. Now all of us know that in many real world situations the birth rate and death rate are not constants due to the instability of the environment. So we have the next model here which is the logistic model, also called as nonlinear model. In this model the birth rates and the death rates are not considered to be constants. So before we go into this model, let us see what is a logistic function and what is a logistic curve. A function that models the exponential growth of a population taking into consideration the carrying capacity is called as a logistic function. A logistic curve is a X shape or a sigmoidal curve that is used to model functions which increases gradually at the first, more rapidly in the second part and slowly at the end, leveling off to a maximum value at the end of the time period. So here we have the graph which differentiates between exponential growth and a logistic growth. So we can see that the shape of the logistic curve is S shape or which is sigmoidal. So the assumptions for this particular model will be a birth rate is not going to be considered. So we take birth rate to be a decreasing function of the population size and the death rate is assumed to be an increasing function of the population. So B is equal to B1 minus B2 n of t and D is equal to D1 plus D2 n of t. In the expression of the simple population growth model, we have substituted the value for B and D and we arrive at the following expression. So this is the basic expression which governs the logistic model. Now again this equation can be arranged as a differential equation and it can be solved to obtain the expression for a n of t. So proceeding in the similar way, taking n of t to the other side, dividing by delta t on both sides and letting delta t tends to 0. We have limit n tends to infinity, n of t plus delta t minus n of t by delta t is equal to b1 minus d1 minus of b2 plus d2 n of t into n of t, which is not a linear differential equation, which is a nonlinear differential equation. Now a b1 minus d1 can be replaced by another constant which is k1 and a b2 plus d2 can be replaced by k2. So we have dn by dt is equal to k1 minus k2 n of t into n of t. Now again proceeding by the similar way, like we separate the variables and integrate it between the limits 0 to t. We have the solution for this particular model to be given by n of t is equal to k1 by k2 divided by 1 plus e power minus k1 by k2 t into k1 by k2 by n of 0 minus 1, where n of 0 denotes the initial population. Now as t tends to infinity, we can see from this solution a n of t tends to k1 by k2. Here K1 by K2 is called as the carrying capacity of the environment. That is the maximum capacity which any environment can sustain. Now let us see how the curve for this particular model is sigmoidal, for which we consider dN by dt, which we have already derived. Dn by dt is equal to K1 minus K2 n of t into n of t, which can be rewritten as K2 into K1 by K2 minus n of t into n of t. And as we can see, the second derivative d square n by dt square is equal to 2k2 into k1 by 2k2 minus n of t. Now, from these two derivatives, that is the first derivative and second derivative, we can discuss that the shape of the given curve or the shape of the population growth curve is sigmoidal. When n of t is less than k1 by k2, dn by dt is greater than 0, which shows that n of t is a monotonically increasing function of t. Now considering the second derivatives, if n of t is less than half of k1 by k2, we can see that d square n by dt square is greater than 0. That is, the growth curve is convex. Similarly, when n of t is greater than half of k1 by k2, that is half of the carrying capacity, d square n by dt square is less than 0. That is, the growth curve is concave. Similarly, when n of t is equal to half of k1 by k2, we have d square n by dt square is equal to 0. And this point usually we call it as a point of inflection. That is the point where a curve changes from concave to convex. Thus we can see that n of t increases at an increasing rate till it reaches half k1 by k2 and then increases at a decreasing rate and approaches k1 by k2 as t tends to infinity. So, the following theory is being depicted in the graph, and we can see from the graph that the shape of the curve governing the population growth in a logistic model is sigmoidal. Thank you all for watching.